Hi Physics 100, this is Dr. Kato. This is the fourth video from chapter 11, and should be the last one, and we're going to concentrate on magnetic induction, which is how motors and generators work, which are really important because motors and generator are the connection between electrical energy and mechanical energy. So if we want to be able to do mechanical work like drive an electric car down the road, use an elevator, use a vacuum cleaner, use a blender, have fans and pumps in our homes, we need to understand just a little bit of how magnetic induction works. So let's start with a simple stationary magnet that you think of that has a north and south pole. So you can think about these guys coming around, back around to form a whole U-shaped magnet. Or you can think about two separate magnets that are brought in contact with one another. If these were bar magnets, then this guy would have a south on this side and this guy would have a north on that side. So the first thing we have to talk about is the magnetic field line. So we always draw the magnetic field lines from the North Pole around to the South Pole. And in the area right between the magnets, we draw them straight. And then we start to hook them around and go in ever bigger and bigger semicircles. So the ones that are the strongest, obviously, are the ones that are the shortest. So the magnetic field is going to be stronger right between this side, and it's going to get weaker as you move out in concentric circles in both directions. Okay, an electromagnet is similar to a stationary magnet, only it gets its electric field. Its electric field is temporary. If you have a coil of wire with a current passing through it, it also acts as a magnet. If I take my pencil here and I wrap a wire around it, okay, and I pull my pencil out, I'd get this kind of spring-like series of wire, this coil of wire. If I attached it to either an AC or a DC electric field, just that wire itself would have a small magnetic field, and I could try to pick up different metal objects with it. If I put a metal core in between, like instead of this pencil being made out of wood on the outside, if this was made out of iron, and again, I wrapped it with wire on the outside, attached one side to the positive end of a battery and the other side to the negative end of a battery, that magnetic core would concentrate the magnetic field and it would be much, much stronger. Okay? The moment I disconnect the electric field, the magnetic field would essentially go off. Okay? I might be able to hold a little bit of magnetism inside the pencil, but probably not. I probably need to have that constant electric field. So there is a connection between electricity and magnetism, and it's the fact that whenever charged particles move in a circular path, they create a magnetic field. So, coil of wire with a current passing through it also acts as a magnet. That's an electromagnet. The strength of the electromagnet can be increased by wrapping the wire around a core of soft metal, like we just talked about with iron. Electric motors and generators take advantage of the connection between the electric field, the electric current, and the induced magnetic field. So here's a drawing of what I was talking about. This is a DC circuit. This is an induction loop. We're purposefully coiling the wire so that we create an electric field. If you think about the electrons coming out the negative side of the battery, here's I, the direction of I would be traveling in this direction through the coils. And there's, interestingly enough, something called the right-hand rule. When you put your hand and you put your thumb in the direction of the electric current, and you wrap your fingers, right, and you wrap your fingers around in the direction of the way the magnetic field lines are going, your palm of your hand will point in the direction of the magnetic field. So that's one of the rules. You don't have to know that, but that's the way that you figure out in which direction the magnetic field would be. And again, we always think of the magnetic field going from north to south. So if I did that, and if I'm doing this right, then the magnetic field would be pointing out of the palm of my hand. Okay, so that's called the right-hand rule. Okay, and I'll double check that. Let's take a look at Faraday's law of induction. When a wire and a magnet are in close proximity to each other, and one of them is moving, a potential difference is induced across the ends of the wire, which causes an electric field to flow in the wire. So in this particular case, we're going to have an electric generator. So what we're going to do is take some cores of iron, and we're going to wrap them with wires around them, and then turn them in a circular motion. Okay, and if you turn them in a circular motion, close to a stationary magnet, right? So that the magnet is not moving, but the wires are moving around the magnet, or vice versa, the magnet is moving around the wires. What'll happen is you'll induce a small electric field. Now, that electric field is constantly going to be reversing itself. Why? Because as the magnet and the coil move, maybe this is better, move around one another, the direction of the electric field is going to constantly be changing. So what you're going to wind up with is, you're going to wind up with a sinusoidal curve that sometimes it's going to go positive, then it's going to turn around and go negative, then it's going to turn around and go positive. And at what frequency? At whatever frequency these two things are rotating around. So if I wanted to create 60 hertz electricity that was going positive and negative at 60 hertz, I would just have to move my fingers around one of them pretty much at 60 times per second. If I move them faster, they may go 100 times per second. So as many times as your hands are moving, that's how many times the polarity of the electric field is going to change. So motors are definitely naturally going to generate AC electricity. The amount of voltage induced is directly proportional to the rate at which the field through the coil changes. So the bigger the magnets, if you have bigger magnets, you're going to create a larger field, so you're going to be able to create a larger voltage, but it's also the rate at which they pass one another. The faster they pass one another, the more the electricity that you're going to be able to make. Okay, so very simple idea. Just wires and magnets in motion can be used to create electricity. Doesn't have to be a circular motion. It can be a back and forth sliding motion. We just don't usually see systems like that because rotation is so natural, and once things start to rotate in a certain direction, there's so much less friction because you never have to turn around and go back. But you could make a linear system that would go positive, negative, like that as well. Okay? So I'm going to post a couple of videos on AC and DC motors that'll probably explain it a lot better than I can. So you are definitely responsible to look at those videos. They'll come right after this last section of notes. Okay, so the last thing we want to talk about is something that occurs is the transmission of electrical energy. So we talked about this back in the last lecture, that there's always going to be losses in lines, and that's one of the reasons why we jack up the voltage of the electricity that we send from the power plant to our homes, because if it has to travel through wires for many, many miles, we want to keep those losses to a minimum. So we can keep them to a minimum of just around 3% if we raise the voltage that the electricity is coming to our town at to 345,000 volts. So if you see the very high metal electric wires that kind of run through or to your town, when you pass those kinds of areas of town and you look up and you see those power lines, those things are at those hundreds of kilovolts. So they're at huge voltages. This way it keeps the current down. And the higher the ratio of the voltage to the current, the less electricity is lost in the transmission. You can only use AC power to use transformers to be able to adjust the voltage and the current to the place that you want to. Okay, so again, they go in opposite direction. Okay, so if you have the same amount of electrical power and you use an efficient transformer, that doesn't have a lot of losses itself, you'll be able to boost up the voltage, and if the voltage goes up by 100%, then the current goes down by 100%. But percent is probably not as good a way of looking at it as how many times the voltage goes up. So if the voltage quadruples, that means the current is going to be cut to 1/4 of its original value, because the power is essentially going to stay the same. So for transformers, transformers must work only with AC power, and you'll see that when you see how the transformer works. Couldn't possibly work with DC. So transformers work with, and they change their voltage changers, or AC voltage changers. So the power that goes into the input side of the transformer is going to be equal to the power that comes out the other side. So there's not going to be very much losses. Now this isn't perfect, okay? But pretty much for our sake, we're going to assume the transformers have no losses. Well, power, we know, is always equal to the voltage times the current, okay? So the input voltage times the input current will equal to the output voltage times the output current. So let's say the total power is 100 watts here and 100 watts are coming out. There's a lot of different ways to get to 100. You can get to 100 by 50 times 2, right? Or you can get to 100 by 100 times 1. You can get to it by 1 times 100, 50 times 2, as long as this times this is always equal to this times this. So usually what happens is, you know 3 out of 4 of these, and I'm going to ask you to calculate the fourth one. So a lot of times it's going to be the output voltage that you are going to calculate. So this is the first of two formulas related to transformers. The input voltage times the input current is equal to the output voltage times the output current. Okay, even more important is a formula that relates to how the transformer actually works. And this is really kind of neat, okay? If you want to see the relationship between the input voltage and the output voltage of a transformer, okay, and you're independent of the current, okay, remember, we know when the voltage goes up, it goes up because the current must have gone down. Well, the way it works is that I'll show you what the transformer looks like, and then you'll see why these terms are important. We need to count up the number of turns on the primary side of the transformer. So the primary side is the input side. So the way that you count the number of turns is you just look at the wire coming into the transformer and see how many times it's wrapped around the primary side. So this is a typical magnetic core, and I have a wire that's coming. This is a voltage supplier, an AC voltage power supply, and I'm telling you the voltage input is 100 volts, so I'm putting 100 volts into it. And all I do with this power supply is send it, wrap it around here once, twice, 3 times, 4 times. So why 4? Just count the number of times it goes through the front. You don't have to worry about the back. It would also be 4 on the back, okay? Because what would happen is the back would have this one up here, but the last one would be missing because this one would only be on the front. So you just have to count the number of lines here. So this one has 4 windings. So the left-hand side of our equation here would just be 100 divided by 4, okay? So you take the voltage on the primary side, the input voltage, and divide it by the number of windings on the primary side. The primary side is the side with the power supply, okay? All right, the secondary side is on the other side, and this one is designed in such a way, that there are more turns of the wire. Now, this wire, guys, never touches that wire. You just induce a magnetic field in this space here, and it creates a current in this wire. These two wires are just in close proximity to each other, and usually they're actually sitting in a transformer oil. Just to keep them, it helps to keep the system cool and stop anything from undergoing any corrosion, okay? So on this side, what do we have? We want to find out what's the output voltage here. So the first thing we need to do, if we want to know the output voltage is, I know the input voltage is 100 volts. I know the input number of turns is 4. I want to find out the output voltage. So let me count the number of turns on the secondary side. So this is the secondary number of turns. So you come down here, look at the transformer picture and say, wow, this one has many more wrappings around it, Okay, so this one is 1, 2, 3, 4, 5, 6, 7, 8 times around the front. So my N secondary is 8. So for our example, we have 100 divided by 4 is equal to what divided by 8? 100 divided by 4 is equal to 200 divided by 8. So this is a step-up transformer designed to do what? Designed to double the voltage that comes out. So if your particular application, you need twice the voltage, then this is the way you do it with this 2-to-1 step-up transformer. Now, you get to choose for your particular application how many times you want to wind this one, how many times you want to wind that one. And the more times you wind this relative to this, you could do 100 times here to every 1 times there. That would make this side 100 times higher voltage. Well, it comes at a cost. What's the cost? The current. The current would have to be 100 times less. You can't create voltage, right? You only have a certain amount of power. This transformer over here has a certain amount of power. So even though I didn't write it, let me give this guy a current over here. Let's say this guy's current, right? This guy's current originally going in was 2 amps of power we're going through. Yeah. Well, if I was able to double the voltage, so now this is 200 volts, this can only be 1 amp because 2 times 100, right? Power is equal to voltage times amperage. 2 times 100 is equal to 200 watts. 200 volts times 1 amp would be 200 watts. So this formula obviously still holds in every single case. This is kind of cool. That's the way you make transformers. Now, usually we know we're stuck with a certain input voltage. It's the line voltage. So most of the time we're solving this equation in this way where we're solving for V out. So how do I solve for V out? Multiply both sides by NS. So NS cancels on this side and I get NS over here. And that's what this formula shows you. So a nice way to write it is the output voltage of a transformer, okay, is equal to the input voltage of the transformer times the ratio of the number of turns. You take the number of turns of the secondary and divide it by the number of turns of the primary. So our example over here, this one would be 8, this one would be 4. 8 divided by 4 is 2. This ratio is 2. 2 times the input voltage, which is 100. 2 times 100 is 200. So again, a 2-to-1 step-up transformer designed purposefully to increase the voltage, again, and lower the current. Okay, now I'm going to show you a couple of more pictures. This is from the Wolfram textbook, page 300. Just talks a little bit about our electric grid in this country. And you guys remember we've had blackouts, right? We've had pretty bad blackouts, like especially in the summertime for weeks and weeks and weeks. I forgot the year that we had a really bad blackout. But the blackout sometimes can extend over the course of wherever the electric grid goes, right? So we have interconnections between all the electricity of all the different power stations, and they're all interconnected for all of these states. So we are part of this huge Eastern Intercontinental Electric Grid. So it is possible, okay, it doesn't happen that often, that some really bad disturbance happens and the whole electric grid would go out, and the expectation would be that this whole part of the country might lose power together. So we have an eastern one, we have a western one. Again, pretty neat. International borders, right? Crosses into Canada. The western one includes these 2 Canadian provinces, right? British Columbia and Alberta, plus Washington State, straight down all the way across into here, halfway through New Mexico. Okay, and then the third one we have in the United States is the United States of Texas has their own grid, which is kind of interesting. Okay, they got to do something different. Check out Europe. You guys can't see the color differences that much, but Europe has 6 simultaneous electric power grids that are operating. So if you're inside one of those grids, this one being the biggest one, sort of all of Western Europe, here England's on a different one, Ireland's on a different one, these Scandinavian countries seem to be on another one, and here's the Eastern European countries and Russia are on another one, and that's probably left over from the Soviet times when they built their electric grid out. Okay, last graph I want to show you. This is kind of neat. This is electric energy demand over the course of a typical 24-hour cycle. So let me read this to you. Typical demand curve shows electric power demand as a function of time over a full day. Note the low demand at night and rapid rise followed by a steady demand into the workday and a peak around dinner time. This graph shows actual data for Great Britain, England, Scotland, and Wales for a day in mid-November. So no air conditioning going on here, right? Because remember, air conditioning is probably the biggest use of electricity. So mid-November, nobody's got their air conditioning on in England and Scotland and Wales. But just like in the United States, this would be the beginning of the day. This would be 12:01, midnight in the middle of the night. So 12:01, some people are still up. Some people, and then everybody's kind of in bed by 4 o'clock, or almost anybody. And lights are off, computers are off, everything's unplugged. Then 6 o'clock comes, everybody gets up, we're all turning our lights on. And then we peak out at about 11 o'clock or so, maybe 10 o'clock in the morning, and then we kind of stay steady throughout the workday. And then at nighttime, we all have to get home to our homes, and we jack up the power, turn everything back on. So the peak time is really just about 5 o'clock in the evening, right? 1800 should be 6 p.m. at 5 o'clock, and then we tail back off, and then we start the next day. So that should be, this point should be equal to that point. Okay, so this is the number of gigawatts that's used on that electric grid. Okay, and that means they have to make more electricity during the peak times of the day, so they have to ramp up production for dinner time. So that's when all of the generators in England, Wales, and Scotland are probably going full blast at this time of the day when they have to meet that huge demand. Does that make sense? Okay. A couple more. Here's a really neat one. Let me blow it up a little bit. Okay, so this is related to, and I was talking about this when we were talking about electric cars a little bit. This is related to if electric cars are eventually going to overtake internal combustion engines, we need to get the amount of megajoules of energy that the fuel contains, okay, versus the megajoules per kilogram that the battery or device or gasoline weighs itself, okay? We need to get that ratio as high as possible, right? So the higher you get that much more energy out per liter or per kilogram. So these ones over here are the liquids. You would put them this way. These guys over here, you would measure the solids. But either way, coal, first of all, gasoline is the winner. You get the most energy per liter or per kilogram out of anything, right? And it's a logistical fuel. You can pump it into your car. It's not especially dirty. Here's ethanol, which is good, right? We put about 10% alcohol into the gasoline. It lowers that ratio, but again, we're growing this. It's a sustainable crop, so that's a good thing. And it almost comes up there with coal, right? Then here's liquid hydrogen, again, but it's hard to keep hydrogen cold. Here's hydrogen in the gas form at 5,000 pounds per square inch. These are lithium-ion batteries, so we need to get lithium-ion batteries up closer to here. Here's nickel metal hydride batteries. Here's how much energy you could hold mechanically by having a flywheel just constantly spinning, right? So you could just keep it constantly spinning. There's energy that could be stored up that way. And here's lead acid batteries, so they're very, very heavy for the amount of energy that they can hold. So this is your typical car battery. Now, right now, we only use car batteries really to start our car, and then the alternator takes over. So it's okay that these are not that efficient, right? We need to get up here. This is the typical kind of battery. I believe you have lithium-ion batteries inside your for your laptops and cell phones. Okay. This is kind of neat. For that peak demand time, right? One method that you could store up the electricity. So here is that graph for the peak demand time. All right, so what do you do for this little area over here, right? For this couple of hours that you need this extra amount of energy, you might not want to build another whole power plant. So what you could do is whatever power plant that you have that might be close to a river or a lake and has a hill behind it, right? Now you want to be close to the power supply, right? So that you don't lose a lot of energy through the transmission lines. But here comes these high voltage transmission lines and they go into this powerhouse. So what happens is at nighttime, you pump water out of the river or the lake, right? You could even do this with salt water. You pump it uphill into this reservoir because you might have extra capacity at nighttime, right? Extra capacity at nighttime because right here, you don't need that extra electricity. And electricity is not easily stored. So you have this, so you keep on burning your fossil fuel or whatever way you're generating the water. It wouldn't make sense to do this with hydroelectric. But even if you had windmills, right, you could then pump this water uphill and then save it for a day that's not windy or the time of the day that you need it most or a really hot summer day when the peak demand goes highest. Then you allow this water to come rushing back down in the opposite direction and turn this around from being a electric motor that pumps uphill to an electric generator that puts energy back into the grid. So this is a method of pumping water uphill to store electricity. So let's read the caption real quick. It says cross-section of pumped storage facility showing the upper reservoir. Piping and underground powerhouse contains the turbines and generators that also serves as pumps and motors. So turbines and generators during the peak time when you want to create electricity, pumps and motors when you're at the middle of the night when there's not much demand and you're pumping the water uphill. Here's a picture of it down at the bottom. This is the Northfield Mountain Pump Storage Project in Massachusetts. Okay, so this is basically a man-made reservoir which can generate over 1 gigawatt of electric power from the gravitational potential energy of water. This lake is obviously uphill someplace, and then when the water comes rushing back down, we extract the energy that turns the turbine. Okay, so that's everything that I wanted to do for this chapter on electricity. Please watch the next couple of videos. I'll post at least 2 videos on how motors work. Thanks.